Okay, so thank you for coming. I'm Paul, I work at Mozilla, and I've always been doing audio stuff there. For a long time, WebAudio API implementation. We started doing this on Firefox 25, released it. It's now Firefox 72 something, so it's been a long time. And at Mozilla, when it comes to audio on the web, we've always been a proponent to let authors write JavaScript or something, direct manipulation of the sample instead of the different style of the WebAudio API where you connect nodes and everything. So we always believed in JavaScript and give more power to web authors instead of forcing a certain style of making music or audio on the web. And so with AudioWorklet, it's now possible. But because the web platform is always evolving, I'm going to show you something that is not exactly new, but was pushed back for a long time because of the Spectre and Meltdown problems of year, depends on how you count, but like about a year or something ago. When it was found, when it was announced, when it was fixed. It depends on how you count. So SharedArrayBuffer will allow us to do log-free programming on the web. Of course, a favorite technique of audio developers for obvious reasons. And we will discuss why, how, and have some demos, and I'm going to release some code so that we don't write the same code, each of us. We can just collaborate and have a very good library. So, coming from a native audio programmer background myself, the tools at my disposal, and in fact not only at my disposal but also necessary. I see five items in my list here. Low latency, true real-time audio inputs and outputs callback. Right? So that comes from the OS, and it needs to be low latency, real-time, so it needs to not jitter. When it needs to be called, it has to be called. You need to return in a certain amount of time that is bounded. You don't want to do anything fancy in it, you want to do the bare minimum, and the duration of this callback needs to be stable across random quantums or calls. Then audio, of course, we have 48,000 or more samples per second to compute, so we need to do them in less than 1 second. So for this, we need to write fast code. So most of audio developers use C++. I like myself to use Rust because I think it's nicer and I work for Mozilla, so it's an easy sell. We don't like garbage collection because garbage collection makes it non-deterministic to execute code. If you're computing a bit of audio and suddenly in the middle you have the garbage collection that poses your thread and immediately you glitch, of course. What you want also is shared memory between threads. You don't want to copy memory back and forth all the time. Maybe it's because you want better cache effects. Maybe it's because you really don't want to copy because it's wasteful in terms of megabytes of memory you have. For example, if you have an enormous sample banks, you really want to have it only once. So then to synchronize access to this shared memory that we just talked about, we like to use atomic accesses and log-free data structures. So that's what we're going to be talking about today in the context of the web. And to make it faster, we like to use SIMD. That's the subject of another talk. We're not going to talk about SIMD today. However, it's possible on the platform to leverage SIMD both on ARM and x86. So AudioWorklet, a little refresher or a little introduction for people who haven't written any AudioWorklet code. So as always, in any audio API, in any audio page that uses the WebAudio API, you acquire an audio context like this. And then it's got the AudioWorklet property. that happens to have a method that's called addModule that takes the URL. So this is, for example, this is a relative URL. So it's just a file name. So it will be fetched. Then it's a promise. So when the code has been downloaded and parsed and stored somewhere in the web browser, we know about it. At this time, we can execute a function and create an instance of the AudioWorklet node with a specific name. And then, as usual in the Web API, you connect the sound-making thing to the destination to hear it in the speakers. So in dsp.js, the file that I just referenced in the previous slide, we just extend the AudioWorklet processor. For example, this is a noise generator, just a white noise. So it's got a constructor that's just going to do nothing but call the constructor of the superclass. And then it's got what is going to be very familiar to any audio programmer is a callback, which is called process. Yeah. You have three parameters, input and output and parameters. Input is going to be the input to the node. Output is going to be where you write your output. You want to communicate it to other nodes. And parameters are regular audio parameters that you can specify yourself. So here, what I do, I just loop over the size of the output. This is a noise generation node, not a processing node, for example. And I just fill my buffer with random values between -1 and 1, which is essentially always nice. So input and output are arrays of 32 array. Because you can have multiple inputs to a node, each input can have multiple channels, and then you have the samples themselves. This is very flexible. You can exactly choose which one you want, what gets shrugged, where, and that kind of thing. And then at the very bottom, we can see here, register processor. Then we give it a name here, and we give it the class. And we can see in the previous example, this is the name we use here. So that's what bridges the main thread, and here is the audio thread. Right? This code is going to run in real-time context, so you need to be careful about what you're doing. You don't have most of what the DOM has. So, for example, you don't have DOM elements. You cannot do images. You cannot do network requests. You cannot do. In fact, you can't do anything but do math, more or less. And we'll see this is not quite true because you can also communicate back and forth between the main thread and the audio thread. So to do this, we have more or less the same code than before here. But we can also, we also see that this node N has a port, and the port supports the post message here. So you can post message anything, can be an object, buffer, float, anything that can be represented in JavaScript. So here I'm doing the classic send the new value when my slider changes, right? So very simple example. I've got a slider of, let's say, the frequency of an oscillator or the amplifier volume or whatever, and just send every new value. How is it communicated back to the audio thread? I've got the same code here. We see that this is the only thing that changes. So on message on the port, this function will get called, and we do whatever we want in it. So for example, here I've decided that I'm going to communicate the volume of my noise generator. The volume starts at 1, so full volume, full scale. But I can set new value here, and then, as usual, to change the volume, we multiply by the gain, and that's about it. So very simple to communicate back and forth. What is the problem, however? The problem, you see, is that every time you post a message to or from an AudioWorklet, that creates a temporary object. This temporary object is going to be garbage collected by the JavaScript engine, depending on the web browser. And any possibility for garbage collection means that the process, I mean, your DSP code is not bounded anymore. So you really want its bounded time of execution, and if you use post message too much, then you create a lot of garbage that needs to be garbage collected, right? we've optimized garbage collection a lot in the last few years, so you can go a long way with with doing post message. It works pretty well until it doesn't. Right? And also, garbage collectors change, their heuristic change. They change between web browsers. So, for example, maybe V8 is faster than SpiderMonkey in some cases, but the opposite is true in some other cases, so you don't know. So why risk it? Right? In audio, you don't risk, you don't really want to risk anything. So we have this new object called SharedArrayBuffer, and it doesn't create garbage, right? So to communicate to SharedArrayBuffer, you post message it once at the beginning, during the setup phase, and then you never post message again. But instead, you've got the SharedArrayBuffer. There's going to be a view on a shared bit of memory from the two sides, main thread or real-time thread. This is a very easy technique. Everybody uses it in native without thinking, I'm sure. But in the web, we don't like shared memory because it's extremely complicated to manipulate. SharedArrayBuffer allows us to do that. SharedArrayBuffer comes with an Atomics API, so you can do Atomics access. Atomics access is accesses. You can do write and reads to memory from different threads at the same time. It's fine. It's guaranteed to work well. So SharedArrayBuffer is like the ideal candidate for what we want to do here. So I'm releasing today this library that's doing exactly what I just talked about. So actually, I need to click here. And yeah, yeah, okay, it's public now. That's fine. One sec. Okay, good. So that's with all the nice stuff. Trying to first read me. Probably lots of typos, you'll forgive me. So ReadBuff.js implements the bread and butter data structure for audio programming on the web. So single consumer, single producer ReadBuffer that is thread safe and weight free. You have the guarantee that any write to the data structure is going to be completed in a bounded time, and you have the guarantee that any read to the data structure is going to be completed in a bounded time. It's very, very useful. In fact, we use this in Firefox, more or less the same algorithm. So it's not particularly complicated. It's not a lot of code, but it's been carefully written and audited by the JavaScript team at Mozilla to ensure that it will never ever create any garbage collection hazards, never ever trigger garbage collection. It will optimize well as far as JavaScript engine is concerned. So this is code that is more or less ready for production. So I've got a few files, more or less intentionally and also not intentionally. There is no packaging or package.json or whatever. So if you're willing to help, clearly I'm not a JavaScript programmer, so I don't know how to do that. So yeah, packaging it up so that it's easier to use when you use a bundler, for example, whatever bundler it is, or a toolchain or something. So we've got a bunch of different files. So there is examples. So you've got the main thread JavaScript file and a processing thread JavaScript file. Then you have the ring buffer itself here. Then you have something that uses the ring buffer but is for streaming audio back and forth between the AudioWorklet and something else. Maybe it is a web worker, maybe it is the main thread. Then you have param.js, which is for log-free parameter changes. So you in the VST framework style, you've got a parameter index and a parameter value, and that's it, right? Very, very, very classic. And then utils.js is just something that they find useful to bundle at runtime in JavaScript, bundle together a number of files and have them loaded in a AudioWorklet. So that's the way, if you don't use a bundler, you can also have a nice development experience and have multiple files in the AudioWorklet. So I try to explain a bit why I'm doing this. It's useful, advice as always. Usually you don't really want to generate the audio on the main thread, you want to do that in the worklet thread. However, in some cases it's very useful. If you're implementing an emulator for an old console, everything is in a single thread, so audio generation happens there. It's very useful to implement emulators. So for example, on archive.org website, you can boot up any old game using JavaScript emulators and play the games from your childhood. It's very nice. Porting code that use push style APIs such as SDL. So quite a lot actually of 2D indie games use SDL, and porting those to the web is very easy if you have access to a push audio API, which is not what we would choose for professional audio software, but there is legacy code that exists, and so reviving this old code by compiling it to the web is nice. Recording what the worklet has seen at its input and sending that off to a web worker to encode or to send it off to a server is also very useful. So certainly you don't want to make network requests in your worklet. In fact, you can't even have access to the API. What you do in fact is you ship the audio in a different thread and you make your request there. So a serious example, what is important in this is ringbuff.js. So I tried, because it's a bit complicated code, I tried to comment it heavily. You see that it doesn't really look like your traditional atomic flow. You would see that in C++, particularly in JavaScript. So it's nice, it works well. Of course, we all like demos, right? So the demo here, I'm just going to show a bit of the source code. It's not, I need colors. It's just a very simple app that is in request animation frame generating the sine wave, right? So you don't do that, by the way, just for the sake of the example. So I'm generating a sine wave, and then I'm enqueuing it to my ring buffer, right? So that's very simple. I'm doing synthesis of a sine wave. The frequency of the sine wave can be changed. So you just change the frequency on the slider. However, the volume of the sine wave itself, you don't generate it directly in the main thread. Instead, you ship the new value to the audio thread. And we'll see here that in the audio thread, it's really quite simple in the process method. So if we can dequeue a parameter change, we get the new amplifier value. And in any case, we dequeue some audio from the ring buffer and we copy it out, applying volume to the output buffer. So it's essentially an audio sync. It's going to play whatever it comes into the buffer, right? So it's a contrived example, of course, but I wanted to have something simple that show how it works, so that the only complexity is, in fact, the usage of the API itself, and not anything else. So, I mean, that's so we can test in Chrome, for example. You recognize this sound here. You can see the parameter change. I have console.log from the audio thread. Don't do this. And we see that this one, every new value is sent off via the ring buffer and applied directly in the audio codec. Whereas the first one only changes the value on the main thread and changes the generation, how the waveform is created itself. But that's Chrome, right? So we can of course also go into Firefox because this is the web, right? And that's it, and we see exactly the same stuff. The console.log works, and so this is completely AudioWorklet SharedArrayBuffer demo working cross-browser. So it's nice. And I'm very happy to answer any question about the code, because I don't like, so if you've been doing that before, then it's fine. The algorithm is very familiar. It can be, yeah, some choices that have been made in these libraries are not obvious, maybe, if you're not from the domain. So I'm very happy to write more documentation or anything else. So as I say again, please contribute. GS dev, I don't know. I know that VR is something that people use, or NPM, or that kind of thing, but that's about it. So for example, I think we need a package.json thing, but I don't know how to write it. The API is strange. There is some reason for this, because the API has to be strange a bit to minimize copies, and also to ensure that there's not going to be garbage collection. So it's not that strange. It's just, you wouldn't necessarily do this in JavaScript, but it's important. That's also, I also want to invite everybody that is here and likes the WebAudio API to join the community group, which is essentially very low friction. Just click 2 buttons on the Productivity website and you get invites when it's time to talk about new standards. And if you want the open feature in the spec, just tell us. If you miss something, we are listening actively, and we are in fact working to have new features in the WebAudio API. But we need community input, because we know what we want. But it's only like 4 of us, 3 maybe. So we have a very narrow perspective and not a diverse point of view. And we can discuss on GitHub, so any change on any spec is just a GitHub issue tracker. Just come in with your GitHub account and yeah, tell us what we did wrong, and write to a platform tests if you're really into that. So it's tests that run in every web browser and check that they are compatible with each other. That's very, very useful. We have an extensive set of tests for the WebAudio API that, of course, no browser passes all of them, but it's getting increasingly close. And it's good to have the confidence to, like, we know it works, because like, all the tests are going all the time, they run on each commit and that kind of thing. And yeah, if you're really, really into it, you can contribute patches to implementation. So I'm very happy to shuffle you inside the crazy code base that is Firefox. We've received very nice contributions over the years on various parts of the audio stack, whether it be a new backend for a new platform for audio input outputs, or lately optimizations for the quality of the speed change for videos, for example, time switching. So it's just 2 examples. And yeah, that's about it. So thanks. Very happy to talk about this library after and its characteristics, and a few links, so you can click those and learn about a bunch of stuff. And very happy to read emails and exchange emails or tweets or whatever. And thank you.